Bismillahirrahmanirrahim. Today we see some more problems of Fourier series on a periodic interval. It is the continuation of the previous lecture. There are a couple of questions which I think it is difficult, so I feel I do it myself. So in this respect, this is our lecture number 12. In this regard, I take question number 9, which I feel it's a little bit difficult. So here the function is f of x is equal to 0, which is in the interval from minus pi to 0, and the value of the function sine of x, which is in the interval 0 to pi. So as previous practice, let we suppose our given interval is minus p to p and its value is equal to, as you see here, this is minus pi to pi. From minus pi to pi, after simplification you get 2p is equal to 2 pi. Then after simplification you get p is equal to pi. And the Fourier series is f of x is equal to a naught plus summation n is equal to 1 to infinity a n cos n pi x over p plus b n sine n pi x over p. And as you know that a naught, a n and b n are called the Fourier coefficients. Here is the values of these Fourier coefficients. A naught is equal to 1 over 2p minus p to p f of x dx, and a n is equal to 1 by p minus p to p f of x cos n pi x over p dx, and the third one is bn is equal to 1 over p from minus p to p f of x sine n pi x over p dx. Now first of all we want to find the value of the coefficient a naught, and 1 over 2p minus p to p f of x dx. Here you substitute the value of p, that is equal to pi. It becomes a naught is equal to 1 over 2 pi minus pi to pi f of x dx, and then you split the integral over the interval as they are given minus pi to pi and then 0 to pi. Here you see I split the integral according to the interval from minus pi to 0. Here the value of the function is 0, and from 0 to pi the value of the function is sine of x dx, sine of x. So this integral becomes 0, and when we evaluate this integral, you get minus cos of x, and then we evaluate this at 0 to pi. When you evaluate this, we get I take this negative sign outside, then I evaluate this cos at pi and 0, and you get cos pi minus cos 0, and you know that cos pi is equal to minus 1, and here cos 0 is also equal to 1. So after simplification you get that 1 over pi. Now we move towards second Fourier coefficient, that is a n, and you know that its value is equal to 1 over p minus p to p f of x cos n pi x divided by p dx. So I substitute here the value of p, that is 1 over pi minus pi to pi f of x cos n pi x over pi dx. At the value of p I substitute here pi. This pi is cancelled with this pi, and you get after simplification f of x is equal to cos n x dx. Now again we split the integral according to the given intervals. So in this way we get the first minus pi to 0. Here the value of the function is 0, as you see here, and then cos nx dx plus from 0 to pi sine x, then cos nx dx, and you know that this becomes 0, and we get 1 over pi from 0 to pi sine of x cos nx dx. And we know that there is no formula that we integrate this integral, that we integrate this function. So we have to convert, convert it a product formula. in this respect we divided by 2 and also multiplied by 2. We divided by 2 and also multiplied by 2, and you know that 2 sine x cos nx, you know it has a product formula that has value 2 sine alpha cos beta is equal to sine alpha plus beta plus sine alpha minus beta. Here alpha is equal to x and beta is equal to nx. So when I substitute this, I put this substitution here, then we get 1 over 2 pi from 0 to pi sine. Here the value of alpha is x and the beta is nx, plus sine at the value of alpha x, then minus at the value of beta it is nx. So we get 1 over 2 pi from 0 to pi sine 1 plus nx dx. I take here x common, then from here sine 1 minus n, taking x common, it becomes like this. So 1 over 2 pi, when you integrate this, it is equal to minus cos 1 plus n into x divided by 1 plus n. From where this 1 plus nx, 1 plus n comes, when you integrate this, you have to take the derivative of the angle and you have to divide with this. So I am doing here minus cos 1 minus n into x divided by 1 minus n, and these are the limits of the integral. So you see here 1 over 2 pi minus 1 over 1 plus n. Now I substitute these limits here, 1 cos into 1 plus n into pi minus cos 1 plus n into 0, then minus 1 over 1 minus n, then cos 1 minus n into pi minus cos into 1 minus n into 0. So we get 1 over 2 pi minus 1 over 1 plus n, and you know that by de Moivre's theorem we also write this formula in this term in this form, cos pi whole raised to the power 1 plus n, then, and you know that cos 0 is equal to 1, minus 1 over 1 minus n, again cos pi whole raised to the power 1 minus n, and cos 0 is equal to 1. So minus 1 over n over 1 plus n, here cos pi is equal to minus 1 raised to the power 1 plus n, minus 1 over 1 minus n, minus 1 raised to the power 1 minus n, minus 1. Now an is equal to 1 over 2 pi minus 1 over 1 plus n, minus 1 raised to the power 1 plus n, minus 1 over 1 minus n into minus 1 whole raised to power 1 minus n, minus 1. And here I am doing this negative 1 has power 1, this negative 1 has power 1. So I am writing here minus 1 raised to the power 1 and then minus 1 raised to the power 1 plus n divided by I multiply these this term with both these terms. I multiply this minus 1 over 1 plus n with this term and this term. So I get minus 1 into minus 1 raised to the power 1 plus n divided by 1 plus n, then minus plus 1 over 1 plus n, and then minus 1 over 1 minus n into minus 1 raised to the power minus 1 minus n, then we multiply this term with this, we get plus 1 over 1 minus n. Here you see that I write this negative 1 as minus 1 raised to the power 1. It is equal to, we write this in this form. Then minus 1 raised to the power 1 plus n divided by 1 plus n. Here you see that I am replace its sign. I write its sign as positive and negative take like this. Minus 1 into minus 1 raised to the power 1 minus n divided by 1 minus n, and the remaining terms are 1 over 1 plus n and plus 1 over 1 minus n. Here you see that I use the exponent rule here. I use the exponent rule here. Bases are same, then you add their powers. When bases are same, then you add their powers, it becomes minus 1 raised to the power 2 plus n. Similarly here, minus 1 raised to the power 2 minus n plus 1 over, I take its LCM, 1 plus n, 1 minus n, it becomes 1 minus n plus 1 plus n. Now, one important thing that I am doing here, you see in the statement of Fourier series, summation runs from 1 to infinity. Summation runs from 1 to infinity, or if we say it runs from 0 to infinity. It takes only positive terms. It takes only positive term, and we know that we are working here on the periodic interval. They are equal on both the sides, from 0 to positive side and then 0 to negative side. The length of the interval from 0 to either positive side and negative side are equal. So we replace here, because the summation sign runs only for positive n, from n is equal to 1 to infinity. So replace minus n, replace minus n by n in the powers of minus 1, in the powers of minus 1. Replace minus n by n in the powers of minus 1, because summation runs from 1 to plus n, 1 to plus n or plus infinity. So in this way I am replace this negative n by positive n, and after simplification it becomes minus 1 raised to the power 2 plus n divided by 1 plus n, this negative 1 raised to the power 2 plus n divided by 1 minus n, and after simplification this n is cancelled with this n, it becomes 2 over 1 minus n square, 2 over 1 minus n square. Now you see here, minus 1 raised to the power 2 plus n comes common, takes common, so we get minus 1 raised to the power 2 plus n, and then I am taking its LCM, it becomes 1 plus n, 1 minus n, and then 1 minus n plus 1 plus n. This n is cancelled with this n, and after simplification we get 1 plus 1 is equal to 2, 2 into minus 1 raised to the power 2 plus n divided by 1 minus n square, and plus 2 over 1 minus n square. Here I take 2 common, I take 2 common, so this 2 is cancelled with this 2, and I am writing here 1 plus minus 1 raised to the power 2 plus n divided by 1 minus n square, and I am also equivalently write it as 1 over pi 1 plus minus 1 raised to the power 2 minus 1 raised to the power n, and you know that minus 1 raised to the power 2 it becomes positive, so the remainings are 1 plus minus 1 raised to the power n divided by pi into 1 minus n square, 1 plus minus 1 raised to the power n divided by pi into 1 minus n square. Now you see here the third Fourier coefficient, that is Bn, that is equal to 1 over p from minus p to p f of x sin n pi x over p dx. Again I am substituting here the value of p here, that is pi, 1 over pi from minus pi to pi, that is f of x sin n pi x over pi, pi is cancelled with this pi. Now I am splitting the integral according to the interval, and you know that one of the value is 0 in the interval from minus pi to 0, so I am not taking that, I am only taking that interval which is not 0. So you see here 1 over pi from 0 to pi sin of x sin nx dx. Again you divided by minus 2 and you divided by minus 2 and multiplied with negative 2, and you know that in this way we get a product formula. So we get minus 2 sin alpha sin beta is equal to cos alpha plus beta minus cos alpha minus beta. So again I am using that formula, and we get minus 1 over 2 pi from 0 to pi cos x plus nx minus cos x minus nx. So here is a problem. As you see here, if I integrate here, you get sine. You get sine here, sine, and when you evaluate the value of the sine at pi and 0, you get equal to 0. And when you use here the sine formula, when you integrate this, you get sine, and when you evaluate this integrand over pi to 0, you again get 0. But at one point this Fourier coefficient is not equal to 0. At one value of n, this Fourier coefficient is not equal to 0 if I substitute n is equal to 1. When I substitute n is equal to 1, you get minus 1 by 2 pi into cos x plus x. I am substituting here n is equal to 1, and here cos 1 minus x, cos x minus x, you see here, and cos 2x divided by 2, and we evaluate it from 0 to pi, then minus cos 0 is equal to 1, and its integral is x. So you see here, when I evaluate this sine at pi and 0, we get 0, and when you evaluate this x at pi and 0, you get pi. So after simplification, you get 1 over 2, and all other values of n, this b is equal to 0 except n is equal to 1. Okay, if I take n is equal to 1, it becomes a non-zero value, and remaining other values of n, all the values of bn are equal to 0. So in this way, required Fourier series is equal to f of x is equal to a naught summation n is equal to 1 to infinity a n cos n pi x over p plus b n sin n pi x over p. When I substitute here the respective values, and you know that a naught is equal to 1 over pi plus summation n is equal to 1 to infinity 1 plus minus 1 raised to the power n, and the value of a n, pi into 1 minus n square cos n pi x over pi plus 1 over 2 sin n pi. Here I substitute n is equal to 1, so that's why I am writing here 1 pi x over pi, and after simplification you get 1 over pi, and you see here pi is cancelled with this pi, and we get 1 over 2 sin x, and this term is independent from summation, so I take it outside from the summations, plus summation n is equal to 1 to infinity 1 plus minus 1 raised to the power n divided by pi into 1 minus n square cos n x. In this way this question comes to end. Now we move towards question number 10. Here it is f of x is equal to 0 in the interval from minus pi by 2 to 0, and the value of the function is cos of x, that is in the interval from 0 to pi by 2. So the given interval is minus p to p is equal to minus pi by 2 to pi by 2. So the total length of the interval is 2p is equal to pi, so p is equal to pi by 2. So the Fourier series is f of x is equal to a naught summation n is equal to 1 to infinity a n cos n pi x over p plus b n sin n pi x over p, and you know that what are the values of a naught, a n and b n, and these are written here. Now first we find the value of a naught. A naught is equal to 1 over 2p from minus p to p f of x dx, and I substitute here the value of p here, that is pi by 2 here, 1 over 2 into pi by 2 from minus pi by 2 to pi plus pi by 2 f of x dx, and you know that in one interval from minus pi by 2 to 0, the value of the function is 0, so I am not writing here. I am take that interval which is not equal to 0. So in this way you see here 0 to pi by 2 cos of x dx, and after simplification I get 1 over after taking integral of this I get 1 over pi sine x 0 to pi by 2, and when you evaluate this sine of x at pi by 2 and 0, you get 1 over pi sine pi by 2 minus 0, and you know that sine pi by 2 is equal to 1. So 1 by pi into 1 is equal to 1 by pi. Now we move towards second Fourier coefficient, that is an, and you know its value is 1 by p from minus p to p f of x cos n pi x over p dx. Now I substitute here the value of p, that is 1 over pi by 2 from minus pi by 2 to plus pi by 2 f of x cos n pi x over pi by 2. When you simplify this, it becomes 2 over pi from 0 to pi by 2 cos x. When you simplify this, you get cos 2nx dx, and you take this 2 inside the integral. The remaining is 1 over pi from 0 to pi by 2 cos of x, and then cos 2nx. Some way I forget this to write here, so I am writing here. This is not a par, this is in the angle, this 2 is in the angle, so cos 2nx. Now you know that the product formula is 2 cos alpha cos beta is equal to cos alpha plus beta plus cos alpha minus beta, and in this step I substitute here the values of alpha and beta here. 1 over pi is from 0 to pi by 2 cos x plus 2nx plus cos x minus 2nx dx. 1 over pi cos 1 plus 2n, after taking common x you get cos 1 plus 2n into x plus cos 1 minus 2n into x dx. When I integrate this, you get some sine 1 plus 2n divided by 1 plus 2n, and from and evaluate this from 0 to pi by 2, and when you integrate this you get sine 1 minus 2n into x divided by 1 minus 2n, and you evaluate this from 0 to pi by 2. So here I am substituting their limits, and after simplification by using the de Moivre's theorem, I write this expression in this form, the above expression in this form: 1 over 1 plus 2n into sine pi by 2 whole raised to the power 1 plus 2n plus 1 over 1 minus 2n sine pi by 2 whole raised to the power 1 minus 2n. And you know that sine pi by 2 is equal to 1, and 1 raised to the power anything that is equal to 1, either it is positive or negative. So you get 1 over 1 plus 2n plus 1 over 1 minus 2n, 1 over pi, taking LCM, and after simplification we get minus 2 over pi into 4n square minus 1. And you also write it as 2 into minus 1 whole raised to the power n plus 1 divided by pi into 4n square minus 1. Now we move towards the third one, the Fourier coefficient, that is bn 1 over p from minus p to p f of x sine n pi x over p dx. After substituting the value of p here, we get 2 over pi from minus pi by 2 to plus pi by 2 f of x sine 2nx dx, and I split the integral over the given intervals, so I am taking only that interval which is not equal to 0. So you get 2 over pi from 0 to pi by 2 cos x sine 2nx, and then I take this 2 inside the integral. It becomes the product formula, and you know that 1 over pi from 0 to pi by 2 cos of x sine 2nx, and you know that its product formula is equal to 2 sine alpha cos beta is equal to sine alpha plus beta plus sine alpha minus beta here. So I substitute here this formula here at this place, and we get 1 over pi minus cos 2n plus 1 into x divided by 2n plus 1 from 0 to pi by 2 minus cos 2n minus 1 into x divided by 2n minus 1 from 0 to pi by 2. When I check this at pi by 2, when I evaluate this value at pi by 2, it becomes 0. When I check this expression at 0, it becomes 1. So upper limit minus lower limit minus of the lower limit and this negative, it becomes positive. So I get 1 over 2n plus 1 plus 1 over 2n minus 1. And after simplification, you see here 1 over pi 2n minus 1 plus 2n plus 1. Its simplified form is equal to 1 over pi 4n divided by 4n square minus 1, and it is equal to 4n divided by pi into 4n square minus 1. Now the required Fourier series is f of x is equal to a naught plus summation n is equal to 1 to infinity a n cos n pi x over p plus b n sin n pi x over p. I substitute here the respective values and you get the final answer here. Inshallah ta'ala, we will meet with lecture number 13 in the next video. Till then, take care. Allah Hafiz.